Hello students, welcome back. So now we will be discussing about some examples of Fajans rule. Okay, so the very first question is find the covalent character okay. So the first set of example that I give you is, let's say, NaCl, KCl, RBCl. Okay, so you have to determine who has the maximum covalent character, or you have to determine who has the minimum covalent character, that is increasing or decreasing order of covalent character. Now, before we actually start with discussing the answers to these questions, okay, let us once again recap what exactly we talked about Fajans rule. Okay, so in Fajans rule we said that Fajans rule deals with something called as covalent character, and the covalent character is directly proportional to the charge and it is inversely proportional to the sizes. Okay, but then size of what? The size of cation. So over here I would just write the size of cation, and it is directly proportional to the size of the anion. Okay, so we have discussed this, that covalent character for an ionic compound is directly proportional to the charge of the cation of the anion, and it is inversely proportional to the size of cation but directly proportional to the size of the anion. So let's start with the first question over here. Now over here, the first thing that we need to understand is that NaCl, KCl and RBCl, all of them are having chlorine as a common anion. So here the only thing that would be dependent upon is the cation. Okay, now if we talk about cations, sodium, it is +1, potassium also is +1, rubidium also is +1. So over here the cation, all the cations that we are going to discuss have the same positive charge. So now the obviously anion is out of the picture, the charge of cation is out of the picture, so the dependency will now solely be responsible on the size of cation, and we know that as the size of cation goes on increasing, the covalent character goes on decreasing. So over here Na will have the maximum covalent character, followed by KCl and followed by RBCl. That would be the correct order over here. Okay, let's try one more. Okay, you could pause the video and try answering yourself. So let's suppose if I give you an example over here, let's say okay, BeCl2, MgCl2, and chalo, let's take CaCl2. Okay, so again let's see what exactly we can get through this. Now over here again, chlorine is the common anion, so there won't be any dependency on the anion. Okay, so we'll move towards cation. Now if we talk about cation, beryllium is +2, magnesium is also +2, and calcium is also +2. So obviously cation also has the same charges, so that dependency is also cancelled out or also out of the picture. The only dependent factor now is nothing but the size. Okay, so we know beryllium will have the smallest size, okay, followed by magnesium, followed by calcium. Okay, now the question might come, how do we know this? Okay, so we know this by looking at the periodic table. Okay, we have already discussed, or we must be aware about it, that as we move down the group in the periodic table, the number of shell increases, so the size also increases. So beryllium has the minimum size, magnesium has the moderate size, and calcium with maximum size. And because of this, I would say that beryllium would give you the most covalent character, followed by magnesium, followed by calcium. So who would have maximum covalent character? It would be BeCl2. Okay, so we'll try one more for practice. Again, I would insist that you pause the video, try doing it on your on your own. Let's try. Okay, so over here we will take NaCl NaBr NaI. Okay, so let's try over here. I would like if you pause the video and try doing it on yourself. Okay, sure, let's try. So if we check over here, now the cation is common, sodium, it's common. So obviously there is no dependency on the charge of cation, no dependency on the size of cation. So the whole responsibility is now on the charge and size of the anion. But if you look closely, chlorine is -1, bromine is also -1, iodine is also -1. So all of them have same charges. So definitely now the dependency only comes down to the size. And as we all know, chlorine, bromine and iodine has the maximum size. So maximum size of the anion, the covalent character is also maximum. The size of anion increases, the covalent character also increases. And therefore what we will say over here is NaI will have more covalent character, followed by NaBr, followed by NaCl. Okay, so I hope this part is clear. Okay, we'll move to few other examples. Let's understand few other examples or few other questions how they can be asked. Okay, now one important thing that I would like to share with you is concept of melting point and boiling point. Okay, so over here understand, when I'm saying that the covalent character for any compound, the covalent character increases. Okay, this means the ionic character will decrease, right? Because see, it has to be in balance. Okay, so if you're saying that a covalent character for a particular compound is more, this means that the ionic character is slightly less. But then understand, ionic bonds are strong bonds, and because they are strong bonds, obviously they would have a huge force of attraction, and because they have a huge force of attraction, the melting and boiling point would be greater. So now when we are saying that the ionic character is decreasing, this also means that the melting point or the boiling point will decrease. Why? Because covalent bonds doesn't have that strong forces. So you don't require that much amount of energy to melt or boil these compounds. Okay, so what we can say over here is that covalent character can be directly associated with the melting and boiling point. So we are confirming that as the covalent character increases, the ionic character decreases, and because the ionic character is decreasing, your melting and boiling point also has to decrease. Okay, one more thing. Let's take one example for this and then we'll go on with the next one. Okay, let's take example ABC only. Here only we'll talk about the examples. So over here, NaCl, does it have the maximum covalent character? The answer is yes. And because NaCl has maximum covalent character, if I ask you, out of NaCl and let's say KCl, okay, who has more covalent character? It's obviously NaCl. So NaCl has more covalent character, means less ionic character, and therefore I would say that KCl is more ionic. So melting point of KCl is greater than NaCl. Okay, or similarly RbCl will have a higher melting point as KCl. KCl has a higher melting point than NaCl. Okay, we'll try one more example. Let's say we have an example something like NaCl and NaI. Okay, let me just check. NaI. Okay, so again in this, obviously we need to first look at the cation. Cation has the most important role. So first we'll talk about cation, but in this case the cation is same. Sodium, both the side is sodium. Obviously the charges would be same, the sizes would be same. So the only dependency now, it boils down to the anionic part. And in case of anion, I know that iodine has a larger size. So higher the size, higher is the covalent character. So NaI has more covalent character. So NaCl will have more melting and boiling point as compared to NaI. Please remember, over here we are talking about which aspect? We are talking about melting points and boiling points. Understand this. Okay. One more very important thing that I would share with you. Okay. Now this thing is a bit interesting, although you don't have this in your CIE course, but then definitely you could use this. Okay, you could use it, and this would be something interesting that you should be knowing if you have already reached this far in the topic of Fajans rule. Okay, so what is the thing that we need to understand is that as the covalent character increases, okay, it also increases the color imparting nature. That means over here what I could say is the color imparting nature also increases. Okay, now remember something very good to understand. When we are saying that a covalent character is increasing, that means it is more likely for that compound to have a colored form. Okay, like for example, if I say NaCl and NaI, NaI has more covalent character, so NaI would have more chances of being colored as compared to NaCl. Okay, let me put it in front of you with few examples. Let's understand. Okay, so let's suppose if I give you an example as okay, I'll give you an example, a very interesting one. Okay, let's suppose you have AgF, then you have AgCl, then you have AgBr, you have AgI. Okay, and now I'm asking you ki rank them as per the darkest color that you would observe. Okay, so again the fact is we need to observe about covalent character. Okay, over here Ag being the common common cation, charges and sizes doesn't matter. So obviously everything comes down to the anion. Again, in case of anion, fluorine is -1, chlorine also -1, bromine also -1, iodine also -1. So everything just lands up to what? Everything simply lands up to the sizes of what? Of the anions. And as we all know, iodine has the maximum size. So the covalent character would be maximum in AgI, followed by AgBr, followed by AgCl, and followed by AgF. And that's exactly what happens. Okay, so what we observe now over here, something very interesting, that AgF is actually colorless. Okay, AgCl, however, is white in color. AgBr is slightly yellowish in color. And AgI is dark yellow. Okay. Now, why is this happening? We can say this is happening because the covalent character is increasing, and stronger the covalent character, obviously we would say more is the color imparting nature of that. Okay, now let me give you one more example just to introduce one more factor that we discussed, and that factor was pseudo-noble-gas configuration. Okay, we had a factor of pseudo-noble-gas configuration. Let me just put it in front of you with few examples. Let's suppose okay, let's say we are talking about pseudo-noble-gas configuration. Okay, and I give you an example as NaCl, and the second one I will give you is CuCl. Okay, so we have two examples, NaCl, CuCl. Now, definitely what we can say over here is both of these compounds have chlorine in common. Okay, Na has +1 charge, even Cu in the other case has +1 charge. So charges are also same, but the sizes are not same. And because the sizes are not same, okay, obviously some one of them will have more covalent character, some one of them will have less covalent character. Now, according to our understanding, Na, who has a smaller size, should have more covalent character. Okay, and therefore we should have said that NaCl should be having more covalent character as compared to CuCl. But please remember, this is not true. Okay, what we actually observe is that CuCl has more covalent character. Please remember this, very, very, very important. Okay, what we said was, this was something that we expected. Okay, in terms of what? In terms of covalent character. So we expected that because the anion is same, we'll move towards cation. Cation Na plus, Cu plus. So the charges of cation is same. Na plus will be smaller in size, so it should have more covalent character, and this is what we expected. But as we all know, expectations hurt. So when we observe it in nature, NaCl usually has less covalent character as compared to CuCl. And why is it so? This is because Cu, if you remember, Cu in +1 oxidation state achieves a pseudo-noble-gas configuration. And because it is achieving a pseudo-noble-gas configuration, let me write it over here, it achieves a pseudo-noble configuration. And because it occupies or it achieves a pseudo-noble configuration, what happens is its covalent character increases. And because its covalent character increases, it is showing more covalent character as compared to NaCl. So this is something that we observe, okay, in terms of covalent character. And obviously now if I ask you a question, now see, CIA would never ask you a question on covalent character of CuCl, okay, or NaCl in comparison, but then CIA would definitely ask you questions, or rather most of the exams would definitely ask you a question saying why CuCl has a lower melting point as compared to NaCl. Okay, and why is it so? Because CuCl is a compound which has more covalent character. So more covalent character, that means less ionic character, and that's the reason it should have less melting point as compared to NaCl. Okay, so that is what the question might come, right? Okay, I'll just give you one more question. Just one question popped out, so I'll just share that with you. Probably, chalo, two questions I'll give you, final two questions, and then we'll call it a wrap. Okay, the question is, determine which hydroxide is more soluble. More soluble in water. Okay, and the options for you is FeOH twice and FeOH thrice. Okay, so you had ferric hydroxide and ferrous hydroxide, and you have to decide who is more soluble in water. Okay, so if you could tell me, you could pause the video and try doing it for yourself. I'll just discuss it quickly with you. Okay, now if I talk about FeOH thrice, okay, we need to first decide upon the covalent character. So OH and OH both are common anions, common charges, common sizes. However, the difference will now come with Fe. Over here, it is in +2 oxidation state. and over here it is in +3 oxidation state. Okay, so now understand, because Fe is in +2 and +3, we know that +3 oxidation state will show more covalent character, right? And because it is showing more covalent character, it will have less of ionic character. And because less ionic character, that means less is the solubility, because ionic compounds have a character that they are highly soluble in water. So FeOH twice and FeOH thrice, if I compare, I would say that FeOH thrice has more covalent character. Okay, and because it has more covalent character, I would say it is less ionic, and because it is less ionic, we will confirm that FeOH twice would be more soluble than FeOH thrice. Okay, now this was one question that I solved for you. One question I would keep it for you, and I would like you to answer it in comments, or I would like you to try this. Okay, the question is, in SnCl2, okay, or let me put it, okay, I'll put it like this: SnCl2 is solid, whereas SnCl4 is a volatile liquid. You have to give reason for this. Okay. The question is, SnCl2 is solid at room temperature, obviously, and SnCl4 is a volatile liquid at room temperature. Why is it so? You will answer it in comments. Okay. So we'll stop over here. These were all the questions, or all the type of questions I would say that can come. Okay, the most important of this would be obviously the color part. Okay, they can ask you in some out of the box questions, and the second one that I would say is the pseudo-noble-gas configuration. Rest everything is a bit simpler as compared to other, and has a bit of less chances coming. Okay, I won't say it won't come, not important, nothing like that, but then it has slightly less chances of coming in the examination if I compare it with pseudo-noble-gas and the color scheme. Okay, so we'll stop over here for today. We'll meet in the next part. Till then, thank you, students.